It should help to review our previous presentation, how newer generation of torches keep debuting in the heavens. With certain sense of symmetry, this similar phenomenon happens in the space on the other side of the ASP. A moving torch landing on a motionless gas cloud must thrust the cloud to move somewhat. The movement of the new torch is thus powered not only by the nuclear explosion of the cloud, but also by the thrust that the cloud inherited from the previous torch. We call this process momentum accumulation. The propelling force produced only by a fusion explosion is a fixed quantity for each unit amount of material. The thrust a cloud received will make the newly born torch move at speed different from what this fixed quantity allows. If the torch just born happens to move in the same direction as the torch that landed on a moment ago, it would have the highest speed among all newly born torches. If it happens to be in the exact opposite direction, however, its speed would be the lowest. The speed for all other fragments out of the explosion would be something in between. Momentum accumulation holds the keys of Hubble's law. The basic idea of Hubble's law is that all celestial objects are observed receding from the Earth, and their receding speed increases as the distance of observation increases. It is the momentum accumulation that forces the newer and newer generation of torches to move with ever-increasing speed if they happen all moving in the same direction. We will have mathematical analysis on this law in some much later episodes. Nevertheless, for a feeling of the speed powered by hydrogen explosion, we can refer to our sun. The prominence ejected from the sun usually possesses a speed between 600 to 1,000 kilometers per second. For such a speed to get reached at, the prominence even needs to overcome the gravely enormous gravitational force from the sun. The speed is so strong that it can sustain the prominence at a height that can easily engulf tens of the planet Earth. If the volume of a torch is large enough, it can have its burning last for a long time. It is said that the burning of our sun can last for another 5 billion years. Therefore, with high speed and long-lasting burning, all torches will highly likely meet some hydrogen gas clouds during its traveling. A mass gathering over a certain size can go through a gravitational implosion and thus produce immense heat. However, the heat so produced may also have high chance to escape. If by the time the imploding body reaches its highest temperature, another large quantity of clouds happen to arrive and has this body encapsulated all over, it would help to prevent the temperature from falling back. Not only this, the newly arriving clouds even add another huge amount of heat to it when they gravitationally clash at each other. A temperature that can trigger a fusion reaction is subsequently reached. All it takes is 0.1 second of time for that temperature to appear. However, how much chance can the nature have for an implosion to meet the encapsulation of a right amount of mass at the right time? Such an extremely rare chance destines the first explosion to have happened at only one location, the ASP, out of the infinite universe. After all this explanation, now, it is time for us to show a picture we have long owed to show. In this picture, no fragment out of any explosion can stay still. All fragments must continue their movement until they are out of our vision. Then the sky becomes squeaky clean. The problem is that the sky can never be so clean, as hydrogen gas is always there and all over. The fireworks in the heavens, once starts, must continue and so is our story.